time. So we said that we have the sphere. We have the torus, and then we have these closed surfaces. Closed means compact, without boundary, of genus 2, 3, 4, and so on. This is a closed surface of genus 0. And this is closed surface of genus 1. Then I said that we have three different geometries: spherical, Euclidean, and hyperbolic. Spherical is clear what it means, in fact. I mean, a surface is a spherical surface, like here, this is a subset of the sphere, the map of India. This is a subset of the sphere here. The only surface without boundary which is spherical is the sphere itself. But I have subsets of the sphere, right? And then the interesting problem is to study the distortion from spherical surfaces to the plane, and this will be the subject of my second lecture today. Okay. Now we said that this is a Euclidean. So here the sphere is equipped with its usual metric, with its round metric. Okay. Here, when I say that this surface is Euclidean, it does not mean that it's equipped with this metric which you see here, which you visualize, which you imagine as a subset of like a donut, you know. The donut is not a Euclidean surface. So what does it mean? What does it mean that this is a Euclidean surface? Somebody can tell me what it means? We more or less talked about this yesterday. I want to be sure that you understand. What does it mean that this is a Euclidean surface?
Quotient of the upper plane.
Yes, it is quotient. This is one property or definition. Yes.
The metric comes from.
Yes, exact. So we said that on this surface, the metric comes from. The metric comes from the Euclidean metric, where I do abstractly this identification between this side, and between this side and this side. It means that each point on this surface. So let's see a point here. There's a small disk around it, which is the Euclidean plane. Okay. So my point now is okay. I drew this. Every point here has a disk around it, which is the Euclidean plane. What happens with these points? In fact, what happened with this point? Yes. So this point, after after my identification, is identified with this point. So here I have this half disk here, and here I have this half disk here. So in the resulting surface, this point also has a disk around it, which is the Euclidean plane. Okay? Now, okay, so what happens here at the corners? What happens at the corners? Exact. So a point on the corner, which I see abstractly as a point on the resulting surface, it has a disk around it, which is the union of these 4 disks glued along. This is glued along this. This is glued along this. This is glued along this, and so on. So this point has a neighborhood. It has a disk around it, which is part of the Euclidean plane. Okay. This is what I mean by the fact that this is a Euclidean surface. Now, let me make a remark. My other easy remark is that we also said that when I identify the size of a parallelogram like this, then I obtain also a Euclidean surface, which in general is not isometric to this one. There's no distance preserving map from this surface to this surface. We talked about lengths of geodesics and so on, because a distance preserving map should preserve the lengths of shortest curves and so on. So what happens here? It's the same thing, and the discussion around these 4 vertices here is the same as before, because here I mean the 4 angles add to 2 pi, right? Let me just say a remark here. What about the general case? What about more general case? You see, I take a quadrilateral like this. Okay, and then I do an identification. I take a Euclidean quadrilateral, and then I do an identification between this side and this side. I must use some homotety, right? It must have some dilatation. So I can make here the gluing. I find something which is not a Euclidean surface. You agree? Because there's no. If I take a point here, then a small half disk around it, a small half disk, they will not glue to give me some neighborhood of some point in the Euclidean plane. I find something interesting. In fact, this will be the domain of projective geometry. You see, where you have lines, you don't have distances in projective geometry. You have only lines, and you have ratios of line and so on. So this is something else, which is very interesting, in fact, but it's not my subject. I'm just mentioning this, and I want to. Okay. Yes, I want to arrive here now to the hyperbolic case, and I want to do the same thing, the same kind of construction. First of all, there's a topological construction of a topological surface. We're talking now about closed surfaces of genus 2, which is obtained by gluing some polygons in the plane. Those of you who had some topology course on surfaces know how to do this. If you don't know, I mean, I will not spend too much time on this, but you take you take an octagon, 1, 2, 3, 4, 5, 6, 7, 8. You take an octagon in the Euclidean plane, and then you identify sides. the usual identification is like this: A, B, A inverse, B inverse, meaning inverse meaning that the arrow is on the other side, and then C, D, C inverse, D inverse. This means that you identify this side by this side to this side following the arrows. You identify this side with this side following the arrows, and so on. You do 4 identifications. What is the result, in fact? The result is topologically, the result is a surface the result is this surface, and there's a picture. A picture which you learn if you have a course on such things. So on this surface, you see you have this curve and this curve, and then you have this curve and this curve. So these curves are let's say A, B. This is A, this is B, and this is C, and this is D. You can do this exercise when you are at home. If you never did it, you cut a paper, or you do something with. Some people do it with fabric, with pieces. You construct this. In fact, you can visualize this very easily if you do the inverse operation. You start with this picture. And then you imagine cutting the surface along these 4 closed curves. And you do it gradually. First, you cut along this, and you try to draw what is the surface you obtain. Okay, and then you cut along the second one, and then you cut along the. You see, it's when you have this torus and you have these. This is A and this is B. Here it's easier to visualize. When you cut along B, you get this cylinder. You can open it. And when you cut along A, when you cut along this cylinder along A, you get this way. Okay? Here it's the same thing, a little bit more complicated, but it's not difficult at all. Now, my question is, okay, so this Euclidean octagon, I have a Euclidean structure here at the beginning, but what happens when I do this gluing? Can I get by chance a Euclidean structure on the resulting surface? This is a natural question, right? So the answer is, well, I get a lot of points. I get a lot of points which have Euclidean disks around them. So the people who live on this surface think that they are in Euclidean geometry. Now I want to glue this side to this side, and I want the result to be a Euclidean surface. So the 2 sides must have the same length, right? So why don't I start with a regular octagon? You see, I want a regular octagon. The only way I can do this is to do this, and then I draw a regular octagon. In this case, there is no question about the fact that when I do the gluing here, I can glue this with this by a Euclidean isometry, and yes, and then the resulting point in the quotient has has a small disk around it, which is Euclidean. So, but there's still a problem. Where is the problem? Yes, the problem is only at the vertices. So all these vertices, you see when you do all this gluing, this is identified with this, because B with B. This is identified with this, but also this identified with whatever, with this, and so on. By this gluing, all the vertices of my polygon are identified to a single point. And this is what you see here, in fact. This is. Okay, so what is the problem with the vertices? In the previous case, which I erased, I had a point with 4 sectors, and the angle adds to pi, so it's in the Euclidean plane. Here, I need the sum of the 8 vertices to be how much? Yeah, to be 2 pi. I need the sum of the 8 vertices to be 2 pi. Is it possible? So each vertex must be pi over 4, right? Do I have a Euclidean triangle with a Euclidean octagon where the angles are pi over 4? Is this possible? No, right? This is not possible. So I try in the yes.
It's not good shaking.
Okay. Thank you. Okay. So in the hyperbolic plane, I can do maybe I can do the same construction, you know, taking lines in the hyperbolic plane, geodesics. I can get a hyperbolic surface. I can get a hyperbolic surface if each angle is equal to pi over 4. The pi over 4 is yes, okay. So last time okay, thank you. So last time we constructed a regular octagon. No, we constructed a regular hexagon, so it's something else. My question now is, if I find in the hyperbolic plane a regular octagon with angles pi over 4, then I'm very happy, in fact. I found a hyperbolic metric on a surface of genus 2. Okay? So the construction is almost the same. Well, no. In fact, let me tell you how you construct this. I used a different construction, but I could have used this construction. Okay, this is my hyperbolic plane. Let me mark 4 points on the boundary, equidistant from each other. This does not mean anything in hyperbolic geometry, because the distance between points on the boundary is not defined, in fact. But for my picture, it is okay. So I take this, and then I construct this. I know that I can construct. Well, I know. I see that there's a very symmetric, with respect to this representation, octagon with zero angles at infinity, right? We talked about ideal triangles, so this is an ideal triangle here, this is an ideal triangle, and so on. Now I have ideal, this is an ideal octagon. And then what do I want to do? This is my center, and then this ideal octagon, I want to make it not a non-ideal octagon, a real octagon in the hyperbolic plane by approaching all the vertices at some equal velocity. You see, I do this in the same way because my picture is symmetric. Then I can do the thing symmetrically. So these I make them come towards the center. 4, 5, 6, 7, 8 in a symmetric way. Now I didn't draw it symmetric, but it should be symmetric. Okay. Then the angles here are no more zero. These are angles in the hyperbolic plane. And the angles, I mean, because the world is like this, the world is ordered, you know, these angles are increasing, right? Here I had zero angle. Now here the angles when this comes towards the center, the angles will be increasing, right? These are pieces of circles until pieces of circles perpendicular to the boundary, until it becomes a very small octagon near the center. And now we said something last time. We said that, hyperbolic geometry, like any Riemannian geometry, is locally a Euclidean geometry, right? So when the octagon will arrive here near this point, the angles will be how much? 2 pi? I don't know the answer. I need someone to be sure to tell me the answer. What is the answer for octagon? We already wrote it there. Pi over 4? Huh? The limit is how much?
Limit is 3 pi over 4, maximum.
3 pi over 4.
Yes.
3 pi, thank you. 3 pi, you are right. So 3 pi over 4 is the limit, in fact. When this octagon becomes very, very small, the angles are 3 pi over 4. So the angles, of course, they increase continuously from 0 to 3 pi over 4. From 0 to 3 pi over 4. So in between, there is an we wanted 5 pi over 4 this. We wanted pi over 4 before. So there is I write it here. So there is a regular octagon in the hyperbolic plane whose angles are all pi over 4. Everybody agrees? And then, I do this construction, and this is it. I find this surface. I find a hyperbolic metric on a closed surface of genus 2. Right? And now, you can vary this construction. This is a little bit more complicated, but you instead, you make, here you have suppose this is my picture. You can change the length of A, change the length of B. You can change all these lengths, you know. The important thing, so you have polygons. Where is it? You have in the hyperbolic plane, you have polygons with which you want to construct closed surfaces of genus 2. So the important thing is that so this is A, B, A inverse, B inverse. You see, I want this to be equal to this length to be equal to this length to be equal to this, and so on. In my picture, they are not equal, but this doesn't say anything because in the hyperbolic plane, this is this here is equal to this line is equal to this line, you know, because as you understand now, when you approach the boundary, visually the distances become smaller. So this is now this is a way. So we constructed one hyperbolic structure on a closed surface of genus 2, but because we took a regular hexagon. But what I'm saying is that you see varying the length, and this is becomes a complicated problem. But there's some literature on this problem, and people, even you can produce pictures on the computer. So let me put a statement here. On a surface of genus, on a closed surface of genus 2, while there exists a hyperbolic structure. This is what we said. This is, you have understood the proof. What I want to say is that, in fact, there exists more than one hyperbolic structure. There exists a family of hyperbolic structures obtained by varying the sides of the hyperbolic octagon. In fact, it is a theorem that all hyperbolic structures on this surface, you can find them like this by doing such a. And then the thing which I want to say, a family. Yes.
When you say length, you mean?
No, hyperbolic length. Yeah. All this is hyperbolic length.
So it's dependent on the angle, right?
Different from what?
But it's dependent on the angle then.
But first, yes, you are right. Yeah, the angles must add to 4 pi. I vary the sides, but I keep the sum of the angles. Sorry. Yeah, you are right. Sorry. This is regular, but I want to keep the sum of the. Angles. Yeah, this is. He is right in stressing on this. I vary the sides, but of course I want the sum of the angles around this resulting point on the surface to be equal to 4 right angles, right, to 2 pi. So on a closed surface of genus 2, there's this family of, and there's a dimension. So the dimension is the number of parameters. The number of parameters, I think you cannot guess them from what I mean, the number of parameters will be, so as I mentioned, I think at the beginning, and this is the dimension of the Teichmüller space of the closed surface of genus 2, right? how many parameters there you have? I don't think you can. So the dimension is the general 6g minus 6, and here g equals 2, so the dimension is 6. So the space of polygons in the hyperbolic hyperbolic plane, the space of polygons where the sum of the angles adds to 2 pi, and where this side is equal to this side to this side, and so on. I mean, according to A, B inverse, B inverse, and so on. If you count them, if you try to count them, if you have a method to count them, it must give you dimension 6. The independent parameters are 6. Okay, so this is one thing which is important.
So can you repeat that statement again? Why is it 6?
Because the general formula for let me write here, the dimension of this, well, either moduli space. You see, moduli comes from a Latin word which means you modulate means you vary. Okay, you make it smaller or bigger, you vary. And this is called the moduli space, the dimension of this moduli space, or Teichmüller space. So the Teichmüller space is a covering of the moduli space. We're not talking about this now, but they have the same dimension, covering space. The dimension of this moduli of Teichmüller space, which is the space of, roughly speaking, this is the space of different hyperbolic structures on this on a closed surface of genus greater or equal to 2 is 6g minus 6. You must count parameters. You must count parameters to find this space. I will show you how to count. There are different ways of counting parameters. So there are many approaches to this problem. This is, let me call this is moduli problem. Moduli problem.
Genus 1, it can vary.
Genus 1, the dimension is 2. It's not given by this formula. You are right, yes, it's not given by this formula. So this is kind of making this precise, in fact, which is not difficult now. We shall talk about this. Is what is called the solution to the moduli problem. And in fact, why is this a problem? Why was this a problem? What is the moduli? In fact, this goes, historically, it goes to Riemann. Riemann was very, when he writes something, he writes just small sentences, and then you must understand what he's. And in one of his papers, he wrote, well, for a surface of genus G, there are 6G minus 6 moduli. This is exactly what he wrote. There are 6G minus 6 moduli. And during at least 150 years, people tried to understand what does he mean by the moduli. Then, by the work of Teichmüller, who gave an answer to this in one of his basic papers. In fact, he wrote 5 papers on the moduli problem, other problems on arithmetic. And the paper begins by, he said that Riemann said that there are 6G minus G6 moduli, and nobody understood this. And now I will explain what does he mean by this. And then he wrote his paper, 200 pages long paper, where he explained all this theory. So this is why it's called Teichmüller space, and this is why it's called moduli problem, and because of Riemann. Okay, so this is yes.
More question about it. If you add functions to that, I mean,
Yes.
can something comment about the dimension?
The dimension becomes greater.
I mean, is there a formula?
Yeah, there's a formula, 6g minus 6g minus 6 plus 3p, the number of punctures.
What is the question?
He said if you add punctures, in fact, if instead of surface of closed surfaces I allow punctures, you have to, in fact, when you say punctures, you have to make precise what do you mean by puncture from the geometric point of view, not just from the topological point of view. Okay, so from the geometric point of view, the most, I mean, the case which everybody considers and which is the most interesting is to have, is to consider surfaces with cusps. So hyperbolic surfaces with cusps. So what is a cusp? Maybe I will explain now what is a cusp. Because I want to say something about cusps. Yes. So this is, and this formula works even for torus with cusps. So what does the formula give for a torus with cusps? It should give 2. Is this correct? No? 6 minus 6? No, so you're right, thank you. This is 2. This should be 2, I'm sorry. For me, 2 and 3 are the same. So this is 2. Yeah, I'm glad I corrected this. Yeah, 6g minus 6 plus 2p.
The other vector is better. So right here, this one.
I can use the other one. Yes, you are right, yes. Yeah, okay. Yeah, this one. Okay, so now so this is a way of constructing hyperbolic surfaces of genus 2. Of genus 3, of course, you must take not only octagons, but you see, you can do the same construction. You can do the same construction. 1, 2, 3, now 1, 2, 3. And then 1, 2, 3, and then 1, 2, and then 3, so on. And you get the number of parameters. You get, I mean, it's a little bit more complicated. You get polygon with many. In Thurston's notes, you have ideas about this. You know, I mean, he gives all the necessary ideas. You have to read and think what he says. Yeah. Yes. Okay. So I want to talk about something. Something else about the construction of hyperbolic surfaces, which is okay. Let me. So now. So we know that in the hyperbolic plane we have ideal triangles. This formula, for what I say, will not work. So this is always for genus G greater than 2. Okay, it doesn't work. It works for genus 1 if I have. It works also, but I'm not sure for genus 0. Let me see now. So I take a hyperbolic ideal triangle, and I take, in fact, 2 hyperbolic ideal triangles. And I glue them along their edges. What do I get? I have taken 2 ideal triangles and I glued them along their boundary components. I get this surface. In fact, I don't always get this surface. And I want to explain to you why. And this is very important to understand, because it will have also this is another way to obtain hyperbolic surfaces of genus greater than 1, of closed surfaces of genus greater or equal to 2. So let us take 2, and I want to draw 2 pictures of ideal triangles. This is one here, and this is one here. So yesterday I discussed with some students here, and they know that an ideal triangle has, in fact, 3 distinguished points on the boundary. Each ideal triangle has 3 distinguished points on the boundary, defined in several ways. One way is that there's an inscribed circle. When I do something, some construction like this for one ideal triangle, then it's true for any ideal triangle, because we explained that they are all isometric. If I take an ideal triangle here, then I know that there's an isometry of the hyperbolic plane which takes this one to this one. All of them are the same. So I take the most symmetric one, which has, by dividing my circle into 3 equal parts, this one and this one and this one, then it's clear that there's a center, and then this comes here. I mean, there are many symmetric things I can do. I have these 3 points. Okay. So now I said I take 2 of these. I want to construct a surface by gluing ideal triangles. By gluing 2 ideal triangles. The best, I mean, the natural choice is that I glue this point to this point, this point to this point, and this point to this point, right? And then I find this, here there's no question that I find this surface here. Now I may glue this point to a point here. I can choose this point because I'm gluing infinite lines. You know, I want to glue by an isometry of the line, by a distance-preserving map of the line. I want to glue two lines in dimension 1, Euclidean or hyperbolic or whatever. There's only one real line. So I want to glue this line with this side. I have all these choices. I can glue this point to this point or to this point and so on. And what I'm saying is that if I glue this point to this point here, then something happens. Something happens, and I will explain to you what. First, I want to, you see, okay. Let's come back to this surface. We had a picture of ideal triangles at the beginning of my class, and we had these pieces of horocycles. You remember? Horocycles. Now, by the naturality of the real world, these points here, these 3 points here are the same as before, the same as the points of the points where the inscribed circle touches these 3 points. So I have now instead I have these pieces of horocycles. So I recall that the horocycles in the hyperbolic plane are these circles circles touching this point at infinity, and there are, I mean, at each point I have a family of hypercycles, and here there is this is called a foliation. We shall talk about foliations. A foliation means just, as I said, a vector field without the direction. So I have this foliation by horocycles, which is very, very important. And I have here my 3 points. Let's say the points are P1, P2, P3. And I am gluing P1 to this point. I am gluing P1 to this point here. And there's also the foliation by horocycles. And now I use the property which I want to use is a property of distances in the hyperbolic plane. You see, you can, as I said, you can make computations in the hyperbolic plane. You use usually you use the upper half space model because there's a nice formula for the metric, which I don't want to recall, but the only thing I want to recall is that, okay, I have now, these are two lines, two hyperbolic lines in my upper half plane converging to the same point at infinity. So, for instance, this is an ideal triangle in the hyperbolic plane, right? This is an ideal triangle. This is another ideal triangle. This is another ideal triangle, and they are all isometric. We already said. So there is a formula now. So yes, okay. And when these two sides converge to a point which is in this model is the point at infinity, the horocycles are these lines. The horocycles in this model, I cannot explain this now because it will take us too much, but the horocycles in the upper half plane model are the circles which are tangent to the boundary, including the horizontal lines, which are also considered as circles tangent to the point at infinity, there. Okay. So a very small computation. In fact, maybe somebody, for those who do not know, somebody can give me the formula for the length element in the hyperbolic plane. What do I have to write here? So ds square equals dx square plus dy square divided by what? Divided by what? Y square. Okay, so it's good. So this formula means that if you want to compute the length of a curve in the hyperbolic plane, the length of a curve like you see, you have done parametrized curves, right? A curve in the plane is parameterized by two components, x and y, and depends on t. And this is for, say, for t equals for t from let's say from A to B. This is my parameterized curves. This formula means that to compute the length of this curve gamma, I just have to compute the integral from A to B of square root of dx square plus, well, dx square of t plus dy square of t divided by y of t, and then dt. this will give me the length of this curve, like you do usually in differential geometry. And so you compute, you use this formula. And what I want to say is that if I have a piece of horocycle here of length, let's say L, and here height h, then the length here will be L exponential of minus h. The thing is that these pieces of horocycles, they grow, they decrease exponentially. The lengths decrease exponentially. You remember the first construction I showed, the construction of a Lipschitz map from ideal triangle to itself. There was a picture which I showed you, which was taken from Thurston's paper. He had exactly something like that. It was a picture with he had an ideal triangle with this foliation by horocycles, and then he had. He said, okay, there's a Lipschitz map from this triangle to itself, where the distance here is t, and I multiply. I send this to the horocycle with sorry, a distance. This is a distance kt, and then I think he had a formula for the contraction here, and the contraction was an exponential. So anyway, this is the formula that you need to know. Okay, so now when you have this, let's do this gluing. We said that we glue this to this. Sorry. This one, I glued this one to this one here. So now there is, and then I have a gluing on the three sides, right? I use a gluing on the three sides. So I have a curve which comes from here to here, and here it will appear on the. I will end up on the upper side, since I'm gluing this triangle to this triangle, right? The curve will start here, right? Okay. And then now it depends what I want to do. Well, it depends on the gluing between this side and this side. Okay, but let's suppose that I'm gluing all the sides by some shift to the up. Then it comes here, and 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 then here, and then here, and then here, and then here. So what is this curve doing here? This curve is what is this curve doing in the resulting space? This curve it's going somewhere to infinity, right? It's going somewhere to infinity, but its length. What about its length? What about its length? Because this is the formula here. So the total length of this curve is a geometric series, right? The total length is a geometric series, but because each time I add e minus h plus the next one, which is up, I have to multiply again by e minus h, which will give e minus 2h plus e minus 3h, and so on. Okay? So the length of this curve is finite. This curve has finite length. And it's going to infinity. So is this possible here? If I imagine my resulting surface as this one, Is it possible that I get a curve whose length is finite but which converges to a point at infinity?
It's unlikely.
Yes, it's unlikely. Huh? Yes. This surface here, yeah, so your friend here says that the surface should not be complete. This surface, when I draw it here, it's a complete surface. A complete surface from the metric point of view. But it cannot be this one which I am finding here, because this surface here is not complete, since there are curves which are finite lengths and which go to infinity. So this is one of the pictures I showed you. There are three shifts now. There's a shift between for the gluing of this side with this side. There's a shift for the gluing of this side with this side, and there's a shift for the gluing of this side with this side. You see, I have three isometric maps, three distance preserving maps from the real line to the real line. If if I glue this is like the zero. This is a zero. If I glue the zero with the zero, if I glue the zero with the zero, there's no problem. I get this result. This is the surface. But depending on if each one is zero or not, I get either a surface like this. So the non-completeness means that these pieces of horocycles are converging to. So it's not a surface with boundary, because I mean the boundary will not come. I had no boundary at all. But the completion of this surface is a surface with boundary. So there are three possibilities of the gluing. This is one. This is two. And here there's this spiraling along the boundary. This spiraling of these triangles along the boundary. This is a consequence of the fact that you see here I get when it is glued to something. It is glued to. So it starts here, then it's glued to something smaller, and something smaller, and something smaller, and then something smaller. This is the second possibility. In fact, I said three, but there are four possibilities. This is the third possibility. This is the third possibility, where the shifts are all of them non-zero. And well, there is this fourth possibility, the first one, I mean the most basic one, when all the three shifts are zero. So gluing two ideal triangles may give me four possibilities. It gives me four possibilities for the resulting surface. Okay? And non-complete, but I take the completion. This is not very obvious what I tell you, that when I take the completion, it gives me a surface with boundary, but I will give you a reference to this. The completion will be a surface with 1, 2, or 3 boundary components. And the length of the boundary components, there's a formula which gives you the length, the hyperbolic length of these boundary components in terms of the shifts, in terms of the 3 shifts. This is somewhere in Thurston's notes. it takes maybe 1 page of explanation, in his notes, 1 page of explanation and so on. And then it was long ago, maybe, I think around 2010, not very long ago. I wrote a paper, a long paper, with one of my students where we explain in every detail this construction. It has to be, if you want, you can read this paper. You can refer to this paper. This is me and my student. Guillaume Terré. I don't remember the title of the paper, but in the title there's something with shift coordinates. These coordinates here, these are, when you glue two ideal triangles, and as I said, you have natural 0 and then natural identification with the real number. Shift means just the translation, so are called shift coordinates. Shift coordinates with something else. Shift coordinates, or maybe there's something else with shift coordinates, but the title contains this shift. So okay, so now we are happy because we have constructed one hyperbolic metric on a closed surface of genus 2. Now we are even more happy because we have constructed hyperbolic structures on this kind of surface. This is called pair of pants. So to see that it's a pair of pants, you must return it. Yes, you must revert it. Pair of pants with geodesic boundary. With geodesic boundary. Let me write some more properties that we know. As I told you, so pair of pants of different kinds. This is by abuse of notation, by abuse of name. This is also called a pair of pants with where the length is supposed to be, the length of this boundary component is 0. Right here, the length is some definite positive number, and here the length is 0. So we have constructed just by using gluings of ideal polygons, of ideal triangles, we have constructed what? Let me say, generalized meaning that some of the boundary components may be 0, generalized pairs of pants of any length of boundary components, including 0, between 0 and infinity. So this is L1, L2, L3. I have 3 boundary components. They may be between 0 and infinity. And now something more.
So
Yes.
I am not able to visualize the boundary. Could you repeat that?
Okay. Well, I will repeat what I said, but then maybe I will say something more. Okay. First, what I said is that. Okay, this is my. when I said that suppose I identify this side with this side and this side with this side with the same shift. So first thing is that this curve will end up here, and then it will end up a little bit up, and then it will end up a little bit up, and so on. And this curve has finite length and is converging to somewhere not in the surface. So right. Now, what you didn't understand is why do I get a surface with boundary, right? So for this, there's a picture, in fact, in that paper I told you about, which we did the exact computations. You see, so we are gluing this, like we are constructing the covering, the universal covering of this surface. Okay, when you glue this triangle with this triangle, and then you come back, you obtain this surface. You obtain some surface, maybe finite or infinite here, with which is not simply connected because it has this loop, right? But now I am developing everything on the universal cover. So I'm gluing different triangles, different ideal triangles. So I start with this one. Okay, I glue this. So I will do it more. I will do it on the other side, but it's clearer in fact. Then here, you see, I am in the universal cover. This is glued to another triangle, right? In the universal cover, I mean, I have only ideal triangles glued to. So this second triangle on this horocycle here is shorter, right? It's shorter by a definite constant, by an exponential. And then this one also is shorter here, and then I get a family of ideal triangles, and I see them. They converge to a line. They converge to and this line is the boundary component. This line is yes. So in French it's the relevé. It's the what you get up when you have a curve on a surface. Then this is called the lift. So the lift of the limit here, the limit geodesic is the lift of the boundary component. Okay, so what I was saying, I was saying that we know how to. Yeah, I started there. I think we have constructed generalized pairs of pants. Now, you see, I know how to construct a pair of pants with, let's call ABC, with arbitrary lengths of boundary components. I mean, if you see this, I mean, if the shift is very small, then obviously the resulting no, if well, there's a formula, in fact, which we have in that paper, of the length of each boundary component, which could be 0 or could be any real number, in terms of these shifts. This is the title of the paper: shift coordinates, ideal triangles, and things like that. Yes. What did you find? What is the title? Yeah, he lost the connection. Okay, never mind.
Shift coordinates, straight lines, and oriental structures for tabular space.
Okay, so shift coordinates, and what?
Stretch lines.
Straight lines?
Stretch.
Straight lines?
Stretch lines.
Stretch lines is what I showed you, the big stretch lines. And
For tabular space.
okay, yeah, it's yeah. Okay, so there's maybe another paper with shift coordinates, because here there's no polyhedral structure. This other, maybe I don't know. Okay, there are one or the other. So anyway, what I'm saying is that A, B, C are, there's a formula for A, B, C in terms of these shift coordinates. Now, well, I take two of these with the same number, same boundary lengths, A, B, C, and I glue them. What do I get?
You're going to glue all three together.
No, I take two of these. I glue them one by one, so A, B, C, C prime, B prime, A prime. If they have the same lengths, A and A prime, B prime, and C prime, I can glue them. I get, as we did before for the Euclidean case, I get a closed surface of genus 2, right? So now I have another method than the polygons. This is a different method for getting this surface of genus 2, in fact. So let's say these are the two pairs of pants. One is above, one is below, and then I can continue. For surfaces of genus 3. So this is one here. This is one pair of pants. This is one pair of pants. This is one pair of pants, and this is one pair of pants. In fact, I have to have, in order to perform this gluing, the lengths have to be the same. The lengths have to be the same, but I have a choice for the twist, right? I have a choice for the twist. So my last question before we stop for now, I gave this formula here, 6g minus 6. Let's forget about the p. The p, in fact, you can do it also with this. 6g minus 6. This formula you can see it from here. So how many? So here g equals 3. How many curves do I have? 1, 2, 3, 4, 5, 6. I have 6 curves. And as we said, for the curves, we can choose the length of the curve as we want, right? And then there is this twist parameter. So I have here I have how many parameters? I have 6 plus 6. This makes 12 parameters for this surface here, and the genus is equal to 3. I hope it works. So 6g minus 6 for g equals 3 gives 12. Okay, so I was correct.
What are the six parameters?
Huh?
What are the six parameters?
The 6, first there are the lengths. The lengths must be the same, and I have 6 lengths, right? And then when I have this, when I want to glue this to another pair of pants with the same parameter here, I have also the choice of turning, the twist. I have the choice of the twist. For each curve, I have 2 parameters, the length and the twist, and it gives me surfaces which are not isometric. I mean, you have to prove this, but the surfaces are not isometric.
For each joining, you have two.
For each joining, I have 2, the length and the twist. So this is, and these are called Fenchel and Nielsen parameters. Fenchel and Nielsen parameters are these twist, are these length and twist parameters associated to the, yes. Yes, you have to prove that you get different surfaces, but you get different surfaces when you glue. They are not isometric. For instance, if you want an idea for this, why you get so you see, if you agree on the fact that which I mentioned before, but I will talk about it later, that the isometry type of a surface is determined by the collection of lengths of its simple closed curves. The lengths of the closed curves determine the isometry type of the surface. So now, okay, I have a surface here. Well, when I say the length of curves, I mean the length of the closed geodesics. Like yesterday we discussed these closed geodesics of the torus, so whether the shortest one must agree, then the next one must agree, and so on. So here, okay, this is a closed geodesic. When I glue according to the fact that the length agrees, I glue. But then now, if I make a little turn, you see I have this other closed geodesic in the resulting surface. I have this other geodesic, closed geodesic. When I change the gluing, then yes, the length must change. The length will change, and this is something you prove. This is something you prove, that the length of this new geodesic cutting it. It can become less. It can become. This length function is convex. This is a general result. The length function is a convex function, and so there could be okay, it's convex. It's like this. So there could be 2 points where the length is the same, but then you take a third curve, and the third curve, the length of the third curve will necessarily be different. When the length of this curve is, then you take, for instance, this one, and then you. This is the part of the technical part of the theory. The length and the twist parameters determine the hyperbolic surface. Okay, so I think it's time to for the cakes. In fact,
Anybody else? I think we have asked questions.
Yes, tell me. Yes, you have questions?
Anyone has questions?
Yes.
So when you say lift, it's the covering.
Yes, the covering. Yeah, to the universal covering.
Yesterday we were doing lifting of mats and parts, so that's what you did to the covering.
Yes, to the covering. Yes.
So, genus 4.
Yes.
One you can keep it in a row.
Why I can keep what?
The holes, for instance.
Yes,
1,
yes.
2, 3, 4.
Yes.
You can also make it 1, 2, 3, 4.
Ah, the points.
The holes.
The holes. Yes. Okay. The genus. Yes.
And I don't see how they still have the same parameters.
Okay. I mean, I think that you are 1, 2, 3, 4. This is genus 4. I don't know why you want it to be like this, but it doesn't matter. It's the same. Yes. So this is the complicated thing for you?
It's the same thing.
Yeah, it's the same thing. Yes. I mean, topologically, it's the same surface. You see, I just move this here, I move it here, I get this.
No, in terms of metric.
In terms of metric, this has nothing. I mean, this you see.
These pictures are not.
Yeah, these pictures are not realistic at all. This is the point. In fact, in hyperbolic geometry, you just can represent a surface, for instance, like this, just to stress on the fact that there is a very, very short geodesic. Okay. You can make also this geodesic very. In fact, it's a question of. It's a question of it's a question of the geometry of the pairs of pants. You see, you start with the pairs of pants. You have a. The pairs of pants which I drew, like this one or like this one, they are all unions of two ideal triangles. And we said that the area of an ideal triangle is some fixed number. I don't know, pi, okay, pi. So since any closed surface, or since this pair of pants is a union of two ideal triangles, its area is necessarily 2 pi. So when I make these very small, then there should be lines which are large, in fact, because the area, it cannot be, I cannot draw it like this. This is not a pair of pants, because the area must be 2 pi. And conversely, if I make, if I have very, very big, boundary lengths, then there should be a very, very small piece of fabric joining them. So you can, I mean, when you tell me, okay, like this, I have a perfect surface. So this is also a hyperbolic surface, but it just it doesn't show the reality. This is upside down. In fact, again, this is usually drawn like this. No, up. And this is a kind of pair of pants which Sullivan calls a bikini. Because if you enlarge the boundary components, then there must be too small fabric.